Welcome viewers to my channel. Heterocyclic chemistry is a very important topic and a subdivision of organic chemistry. And it covers more than 50 million, that is 50 into 10 to the power 6 number of organic compounds which are registered in chemical literature so far. So this is a very vast topic, and today I will talk about the basics of heterocyclic chemistry. To begin with the definition of heterocyclic compounds, you can see here four cycles. The first one of which is named as carbocycle, where there is no X, Y, and Z. This is only made up of carbon atoms. Heterocycles are cyclic compounds in which at least one constituent atom should be a heteroatom. Now, what we need to know is what is a heteroatom. Heteroatoms should be those atoms in the periodic table which are nonmetals and having at least one lone pair of electrons. So with the definition, we can have a selection of heteroatoms such as oxygen, sulfur, nitrogen, phosphorus, selenium, halogens, and so on. For practical purpose, most used heteroatoms are oxygen, nitrogen, sulfur, and in some cases phosphorus and selenium as well. So the rest three cycles that you can see here, as you can see, they constitute at least one of X, Y, and Z. So there can be more than one heteroatom in a structure and the compound will be known as heterocycle. Now you can see here in a box four different compounds. First is colchicine. Now here you can see in this molecular formula of colchicine there are several heteroatoms, oxygen and nitrogen, although none of the heteroatom constitute a ring structure. Therefore, instead of telling that a heterocycle, this is actually an alkaloid, and it should be considered as such as the presence of the basic nitrogen atom, and this is a natural product which is obtained from a small plant and used as anti-gout agent. Whereas in the right hand side you can see three different compounds, namely glucose, glutaric anhydride, and adenine. Now theoretically all three of them should be heterocycle because one of the constituting ring structure, one of the atom is heteroatom. However, they are in principle more known, glucose is more known as a carbohydrate, glutaric anhydride is an anhydride, and adenine is known as nucleobase. That means their properties of those individual type overshadow the properties of heterocycles. And in literature, they are prominent as, for example, glucose as carbohydrate, glutaric anhydride as anhydride, adenine as a nucleobase. Now, before I move, I want to mention one thing, that the heterocycles can be classified as aromatic or aliphatic, which can be partially or fully saturated. Now here I will focus on aromatic systems only. And we need to know that these heterocycles are very important and a large proportion of natural products contain them. Many pharmaceuticals and agrochemicals contain at least one heterocyclic unit. And these systems are important building blocks for new materials possessing interesting electronic, mechanical, and biological properties. We can broadly classify the aromatic heterocycles upon their ring size, maybe 5-membered, 6-membered, or larger ring heterocycles. Here I will discuss first about the aromatic 6-membered heterocycles. Here you can see the isoelectronic carbocyclic analog for them. And in the right hand part, we see what happens when heteroatoms being included into the molecular structure. If there is only one nitrogen atom, this is known as pyridine in the six-membered aromatic carbocycle. If this is oxygen, it is known as pyrrolium salt. If there are two heteroatoms and they are nitrogen atoms at 1 and 2 positions, this is known as pyridazine. If the two nitrogen atoms are at 1,3 position, known as pyrimidine, and also if they are at 1,4 position, it will be known as pyrazine. For naphthalene analog, we see this can be quinoline and isoquinoline depending on the position of the nitrogen atoms, and also it can be chromane or chromine if the oxygen atom is incorporated into the molecular structure. These are the common aromatic five-membered heterocyclic structures. In the first column, you see when one nitrogen atom is there in the five-membered ring structure known as pyrrole, two nitrogen atoms at 1,3 position in the five-membered structure known as imidazole. If two nitrogen atoms are at 1,2 position, they are known as pyrazole. And now, if the pyrrole is fused with a benzene ring and forming the heterocyclic structure known as indole. In the second column, we can see oxygen atom as the heteroatom in the five-membered structure known as furan. If in the structure of five-membered ring, there are two heteroatoms, one being oxygen, another one is nitrogen, and they are at 1,3 position, that will be known as oxazole. If the oxygen and nitrogen atoms are at 1,2 position, it will be known as isooxazole. And like indole, if the heteroatom is oxygen and furan is fused with the benzene ring, it will be known as benzofuran. Third column, sulfur atom is there in the heterocyclic structure known as thiophene, and if in addition to sulfur there is nitrogen atom and they are at 1,3 position into the five-membered structure, this will be known as thiazole. And if nitrogen and sulfur are at 1,2 position, they will be known as isothiazole. Also, if we have a fused heterocyclic structure, when furan can be visualized to fused with benzene, this will be known as benzothiophene. Now, before to proceed further into the domain of heterocyclic synthesis and study their properties and reaction, we need to learn some important functional group chemistry like imine chemistry, enol and enolate chemistry, enol ether chemistry, enamine chemistry, such and such. And in addition, we should also learn about some heterocyclic structures which are to be said as the building blocks and will be used for the synthesis of different heterocyclic structure in future. So first I will talk about the imine chemistry and its formation. As you can see, the carbonyl compound when reacts with a primary amine in presence of some acid catalyst, it forms imine. So the imine is a functional group or chemical compound having carbon-nitrogen double bond. Now, depending on the nature of the attached R groups, the regiochemistry of the double bond will be decided. And also, we can have different aldimines and ketimines. For example, if R1 and R2 of this imine compound, any one of the R1 and R2 is hydrogen atom and R3 is also hydrogen atom, then it should be named as primary aldimine. If any one of R1 and R2 is hydrogen and R3 is an alkyl group, then it should be named as secondary aldimine. Again, if R1 and R2 both are alkyl groups and R3 is a hydrogen atom, it should be known as primary ketimine. And if all the alkyl groups, that is R1, R2 and R3 are alkyl groups, then it will be known as secondary ketimine. Notably, sometimes aziridines are also considered as imine equivalent. Now, it is very important to understand 3 points. First, the removal of water is usually required to drive the reaction to completion. And if a dialkyl amine is used, the iminium ion that is formed cannot lose a proton further, and we will have an enamine. Thirdly, the nitrogen atom can be attached to a hydrogen atom or an organic group or alkyl group, rather say. If this group is not a hydrogen atom, then the compound can sometimes be referred to as Schiff's base. Next, we learned about enols and enolates. As you see, the keto form can tautomerize to an enol form. The condition is it has to have an alpha hydrogen atom which is enolizable. And in the right hand part, you can see the formation of enolates from the same ketone only in presence of a base. Now here I must mention that the enol form is favored by a conjugating group which is R2 here, and that may be ester, ketocarbonyl, cyano, nitro, etc. Secondly, we need to avoid the confusion related with enols and enolates, and for enols it is generated under neutral or acidic conditions, where the enolates which is formed in alkaline or basic condition, and the deprotonation of enolizable ketones, aldehydes and esters gives enolates. Another thing, the enolates are nucleophilic through carbon or oxygen center but react with carbon electrophiles through carbon center only. Another important functional group chemistry is enol ethers. An enol ether is an alkene which with an alkoxy substituent. They are electron-rich alkenes by virtue of the electron donation from the heteroatom via pi bonding and have oxonium ion character. As you see here, that under the acidic condition, the ethereal oxygen get positive charge as it involves to bind with a proton via carbon center. And the following species can further be transformed into acetal on reaction with alcohol and to carbonyl compound on hydrolysis. Next, I will talk about enamine chemistry and how it is formed and how it reacts. The condensation of an aldehyde or ketone with a secondary amine produces an unsaturated compound which is known as enamine. These are versatile intermediates and can be considered as nitrogen analog of enols. And in sense of reactivity, they are more nucleophilic in nature and can function as enolate equivalents. However, they require less acidic or basic activation for reactivity. Again, the removal of water is the driving force for the reaction to completion, and this removal of water can take place by distillation or by trapping of water molecule. The enamines can react readily with carbon nucleophiles through the carbon center, and the greater reactivity offered by the ketone enamines than their aldehyde counterparts. As I have said before, now we will learn about some common building blocks, and which will have heteroatoms. And here we go, that it can be urea, it can be guanidine, beta diketones, beta ketoesters, carboxylic acids, amides, amidines, and there are other sulfur containing building blocks also which can be obtained from the carbonyl compounds reacting with phosphorus pentasulfide. And the heterocycle synthesis will require the carbon oxygen and carbon nitrogen bond formation, where we have to use the imines, enamines, acetals, enols and enol ethers whose chemistry I just had discussed. We have to use that. Important point is the CC bond formation, which will involve the enols, enolates and enamines specifically. And during the heterocycle synthesis, equilibrium is driven to the product side because of the removal of water, which is very important driving force for the reaction to completion, and the cyclization of product and the product stability, which can be determined by gaining the aromaticity. Now we move on to the general strategies for heterocycle synthesis with the knowledge of functional group chemistry and several heteroatom containing building blocks in our hand. Now it is quite known that 5 and 6 membered rings are easiest to form. We know from Bayer's strain theory that these ring sizes suffer least strain and therefore are more stable and formed easily. Here, the CX bond formation requires a heteroatom nucleophile which need to react with a carbon electrophile. Now the ring construction, we can have two common addition approach like 1,2 addition and 1,4 addition, as you can see over here, where X and Y can be these heteroatoms. Another important way to manipulate the oxidation state to obtain unsaturated aromatic heterocycles from saturated analogues. Like here, from the hexahydro compound, uh, by means of oxidation, we can have the tetrahydro 1, and which on further oxidation can produce the dihydro compound, and finally further oxidation can lead to the aromatic heterocycle. Now, this unsaturation is often introduced by elimination, like dehydration or dehydrohalogenation process. Four synthetic strategies will be involved for the synthesis of aromatic heterocycles. Among them, 4 plus 1 strategy and 3 plus 2 strategy will be used for the synthesis of 5-membered aromatic heterocycles, and 5 plus 1 strategy and 3 plus 3 strategy will be used for the synthesis of 6-membered aromatic heterocycles. Now to begin with the 4 plus 1 strategy, you can see the retrosynthetic approach to obtain the logical synthones and how they proceed for the forward reaction with easy available synthetic equivalents of those logical synthones. For example, the 1,4-dicarbonyl, when reacts with ammonia and upon dehydration it gives pyrrole or its derivative. Similarly, if we choose suitable substrates, we can get the imidazoles and its derivatives as well. So with this strategy, we can incorporate more than one heteroatom into the molecular structure of 5-membered heterocyclic system. Now for 1,5-dicarbonyl compounds which can be prepared by the Michael additions of enones may be used in the 5 plus 1 strategy. And when the 1,5-dicarbonyl reacts with ammonia and upon dehydration followed by further oxidation may lead with the formation of pyridine derivatives. So 3 plus 2 strategy can be utilized or implemented in order to synthesize the 5-membered aromatic heterocycles, and these are logical synthones obtained after retrosynthetic analysis for them. Again, 3 plus 3 strategy can be used for synthesizing 6-membered aromatic heterocycles, and these are the logical synthones obtained after the retrosynthetic analysis. And there are given some examples for the 3 plus 2 strategy and 3 plus 3 strategy, the synthetic equivalents of those logical synthones. And as you can see, the imine, the enamine, the amino alpha amino carbonyl compounds, 1,3-dicarbonyl compounds, those can be of commercially available synthetic equivalents that can be used in a 3 plus 2 strategy to synthesize 5-membered aromatic heterocycles. And for 3 plus 3 strategy, you can see the enols, the alpha halo carbonyl compounds, and the enols as well. So these can be used as the synthetic equivalents or the starting substrates for synthesizing six-membered aromatic heterocycles. Thank you, viewers, for watching, and hope you like this video and learned something. And I will be sharing more such videos, especially next few will be on the heterocyclic chemistry to give you a complete outlook about heterocyclic chemistry that we practice usually. So please don't forget to subscribe my channel to get more videos like this in future.